This is my Physics 2212 Lab 4 Magnetic Braking with Faraday. So, the purpose of this lab was to collect the data of a magnet falling through a tube of aluminum foil, to model the magnet and tube interaction computationally, and compare your computational predictions with observed data. Some fundamentals are that Faraday's law, which is to the right, Newton's second and third laws, Ohm's law, magnetic force on a loop, and magnetic flux. And some of these are found to the right. Some experimental details were that the model assumes that the magnet falls with the north pole facing downwards. We need to consider the force of gravity on the magnet. The system includes the magnet, the aluminum tube, the surroundings, which is everything else. F1 on the chart to the right, or not chart, but like diagram, is like the magnetic force on the loop, and F2 is the force on the magnet by the loop. Assumed things are that the only forces acting on the magnet are the magnetic force from the loop and the force of gravity. So for the experiment, I used the magnetometer to mark the north pole of the magnet, then I dropped the magnet through the tube and recorded this. I repeated this for 5 trials, and then I calculated the average fall time. The exact fall times are in the chart to the right. The data that I found was that the tube length was 0.3 meters, the tube width was 0.005 meters, the tube's inner radius was 0.02 meters, the tube's outer radius was 0.03 meters, and then the magnet mass was 0.025 kilograms, and the average fall time was 1.21 seconds. So here's part of my coding. In the top, I entered the length, the width, the inner radius, and the width plus the inner radius, which is just the radius. And then in the bottom, I'm creating the ball magnet, and there's some of the code I do that. In the top right, I calculate the magnetic flux, and that's some of the code I do that. So here's the results. In the picture, you can see it's the directions of the things falling down with the magnet, and then the graph shows the big dip, and then it flattens out, and then there's another big dip. So the analysis is that red was it going counterclockwise, and then the blue ring was it going clockwise, and we know this through Lenz's law. If you flip the magnet, nothing happens to the dynamics of the system other than the current directions would flip. The real world and computational systems are close to each other. It would be much more accurate if the tube was split into rings, or if mu was found in a more accurate manner. And the shape of the graph tells us that for the first dip, gravitational and magnetic forces are unbalanced. When the graph levels out, the forces are more balanced, which leads to the flat section. And then when the magnet falls out of the tube, the forces are unbalanced, which leads to that dip again. Some sources of error are human error in measuring the drop time and potential contact friction between the magnet and the tube, and air resistance. And then for the first what if, nearly zero resistivity equals nearly zero resistance, which equals a large current. So the magnet would fall a much slower speed and almost float. And then for the second what if, it would disrupt the rings of the aluminum tube, creating reducing the induced current, which would reduce the magnetic force on the magnitude. This would mean that the time it takes for the magnet to leave will decrease, as the magnetic force would be much less than the gravitational force.